Hello YouTube, new place, new wipe-off board, still no name. So last time we left off on one of the most uninteresting cliffhangers of all time. Huh. I'm alive. I'm hungry. I asked what happens when the x squared term and the y squared term are different coefficients. What do you think happens? Anybody? Anybody? Dealer? Well, here's an example of one. X squared minus 4x plus 4y squared plus 8y minus 28 equals 0. Very convenient this provisional math test comes with examples. Anyway, let's treat this like the other conics we know. It's not a parabola because both these squared guys are in here. It's not a circle either because these coefficients are different. Who cares? We'll treat it like a circle anyway. Alright, the constant goes over to the right to be a loner, the x's group together, the y's go out in a date. You factor out the leading coefficient, that's this big 4 right here. You complete the square, not forgetting to add the extra, which in this case is 4 because it's being multiplied out inside of the parentheses. What do you end up with? X minus 2 squared plus 4 times y plus 1 squared equals 36. Now we come to a crossroads. Normally we divide both sides by whatever the coefficient is in front of the x and the y, but they aren't the same this time. If we divide by the 1, we're back to where we started. Divide by 4, and you're stuck with a 1/4 out of nowhere. We're gonna have to try something new. Fight the man! I was thinking by dividing by what's on the right, but violence is always an answer. If we divide by what's on the right, in this case 36, we'll end up with x minus 2 squared over 36 plus 4 times y plus 1 squared over 36 equals 1. We can simplify this by canceling out the 4 here, pow pow, and you get x minus 2 squared over 36 plus y plus 1 squared over 9 equals 1. What does this look like? The center is at 2, negative 1, as you might expect from our video on circles. Now, just trust me on the next part. I'm going to draw the 4 points that I'll connect, kind of like I did with the circle. Along the x, it's going to be 6 to the right and 6 to the left, and 3 up and 3 down. Connect them, and what does it look like? It's football head! No, it isn't. Holy crap, it is! Hey, Arnold. Anyway, this shape is called an ellipse. Mathematically, you can sketch it by looking at its formula, which will always be in some form like this, set equal to 1 on the right. The square root of this denominator underneath the x will tell you the radius along the x direction, and the square root of this denominator underneath the y will tell you the radius in this direction. Naturally, if b is bigger, then it'll be stretched vertically instead of horizontally. I don't know celebrities well enough to name that sort of shape. Captain Picard. Yes. Regardless of which direction it goes, the biggest diameter from one end of the ellipse to the other is called the major axis, and the shortest diameter is called the minor axis. Just as half the diameter of a circle is called the radius, half of these lengths are called the semi-major axis and the semi-minor axis. These are the numbers a and b that come from your original equation. So what are ellipses used for other than Hey Arnold and Captain Picard? No, that's an ellipsis. What a dork. Ooh, shiny. Kind of like how every point along a circle is the same distance away from the center, every point along the ellipsis has the same combined distance from 2 points called foci, which is the plural form of focus, if you remember those from our talk on parabolas. Good talk! Anyway, if you draw lines from any point to both foci, the sum of this distance will be the same for every point along the ellipse. Doesn't matter where you draw it from. This also means that inside an elliptical reflector, everything emitted at the focus will pass through the other focus. So what? This actually leads to a couple interesting points. There are these rooms called whispering galleries, where you can talk very quietly, even whisper, in one point, and hear that person clear as day in another spot. And this is because of the acoustic characteristics of the elliptical room. Now, some of these examples include St. Paul's Cathedral and the National Statuary Hall in the U.S. Capitol building. It's even said that John Quincy Adams could spy on his Congress contemporaries just by standing in the right spot and listening to the other people at the other focus of the ellipse.
Actually, the architecture that made this resonance possible was not constructed until the 1900s, so John Quincy Adams never could have.
Did I say that I wanted a historically accurate personality? Because I, have enough of an identity crisis as it is! While ellipses aren't a great help for Ben's multiple personalities, elliptical reflectors were once used to pulverize kidney stones, by placing a person inside with the position of the kidney stone at the location of the focus, concentrating the waves in that spot to break apart the painful deposit. The orbits of the planets, or comets, moons, pretty much anything in orbit, follow an elliptical pattern. For example, the Earth orbits around the Sun with, get this, the Sun at its focus. Now, why is that? Because of math. Duh.
Okay, fine, but how do you know where the focuses are?
You mean foci. Well, here I approximated where the foci would be on a general ellipse. They will always be positioned along the major axis, so all we need to do is find out what distance away from the center they are. Remember how we said all points are the same combined distance away from the two foci? Well, look at this point here. It's this far away from that focus, and it's this far away from this focus on the right. Since this smaller distance is the same distance as this one, yay, symmetry! The total combined distance of these two equals the distance of the major axis, which in this example is 2a. Now some geometry. I'm going to pick this point where both distances from the foci are equal. That would make each one a length of a, since the two add up to a total of 2a. We also know this distance because it's written in the equation as b. Now all we need to do to find this is find this length, which I'll call the focal length, or f. The Pythagorean theorem tells us f squared plus b squared equals a squared, which simplifies to f equals the square root of a squared minus b squared. This works for all horizontal ellipses, so whether you memorize this formula or remember the intuition behind it, you should be set. Let's try it out with this equation from the beginning. X minus 2 squared over 36 plus y plus 1 squared over 9 equals 1. We know a squared is 36, and b squared is 9, so the focal length is the square root of 36 minus 9, or 5. That means we're going to go up from the center along the major axis, out 5 in this direction, and out 5 in the other, giving us focal points of 7, -1, and -3, -1.
What about vertical ellipses, smart guy?
Well, it's the same basic idea with Pythagorean theorem, only f equals the square root of b squared minus a squared. Basically, just flip the order. Before you get freaked out about memorizing that, it's just a bigger one minus a smaller one. If you end up with a negative number, do it the other way, because you can't take the square root of a negative number.
No, but I can't.
Oh, I'm ashamed to myself and my family. I should just end this before it gets any worse. Summary. Do the same thing as circles, but divide by the number on the right. The square roots of the denominators tell you how far to go in the x and the y direction. Ellipses do stuff, and the foci are along this major axis with distance away from the center. There's the square root of a squared minus b squared, or b squared minus a squared, whichever one is the positive real answer. Well, if there's a minus sign instead of a plus. Oh, shoot. I guess we have another cliffhanger. Ah! Ooh. Yummy. Thanks for watching. Take care. Ah!